Hello, my name is Michael and this video is about photoelectric effect, photoelectron spectroscopy and photoelectron microscopy.
The photoelectric effect occurs when a material, such as a corroded steel plate, is exposed to high-energy electromagnetic radiation. This causes the electrons of the sample atoms to be kicked out of the material. These electrons are called photoelectrons and their energy depends on the energy of the exciting primary beam, on the binding energy of the electron, and on the work function.
This means that if our exciting radiation has a well-defined wavelength, we can get information about the material's composition and even chemical state if we measure the energy of the emitted photoelectrons. The material characterization method that does exactly that is called photoelectron spectroscopy.
The exciting X-ray radiation can penetrate tens of microns deep into the substrate and generate photoelectrons at various depths, as long as it has sufficient energy. Some of these electrons will never get out, as they lose all their energy by interacting with the material. Other electrons may escape, but as they lost energy in interactions with the material on their way out, they no longer carry usable information about the material. Only those photoelectrons that were generated near the surface, at a depth of only a few nanometers, can escape without further interactions. Therefore, these photoelectrons carry information about the material's composition and chemical state and are used in XPS studies. This makes photoelectron spectroscopy a very powerful material surface characterization method.
So it's perfect for surface studies, but we may not get information about the bulk material itself.
In a real system, the measurements are done in ultra-high vacuum, where the electromagnetic radiation with well-defined wavelength is generated with an X-ray source, such as an X-ray tube or even a synchrotron. The energy of the photoelectrons is studied with the help of a hemispheric electron energy analyzer. Inside the analyzer, electrical potential is applied between the inner and outer wall. The inner part has a positive potential, so it attracts the negative electrons. The outer part has a negative potential, so it repels the negative electrons. Only electrons with specific energy can pass through the analyzer and reach the detector. If the energy of the photoelectrons is too low, then they are pulled into the inner wall and therefore they never reach the detector in order to create a signal. If the energy of the photoelectron is too high, however, then they hit the outer wall instead. If the electrical potential is just right, then the electrons can pass through the analyzer and create a signal as they hit the detector. In real systems, the hemispheric electron energy analyzer lets through photoelectrons in a specific energy range. Within this energy window, the precise measurements are done with the help of electron optics that either accelerates or slows down the emitted photoelectrons and then guides them to the analyzer. So the XPS spectrum is obtained by using the electron optics to scan through the energy window that was selected with the hemispheric electron energy analyzer. The detector itself is based on an electron multiplier, where a high voltage is applied between the front and the end. Each diode inside is 100 to 200 volts more positive than the previous one. An electron which enters this system is accelerated to the first diode, where it kicks out electrons. Those electrons now move to the second diode and kick out even more electrons, which leads to an electron avalanche that is collected with an anode. As a result, a current pulse is measured. In newer CCD detection systems, the electrons are multiplied again in a multiplier, and when they hit the phosphor screen, photons are created. Those photons are then captured with a digital camera. Now this marvelous piece of engineering is a real X-ray photoelectron spectrometer used for surface studies in the Institute of Physics in the University of Tartu. It operates in ultra-high vacuum of 10⁻⁻10 millibar, which is obtained by combining oil-based rotary pre-vacuum pumps, a turbomolecular high vacuum pump, and finally an ion pump for ultra-high vacuum. Here is the X-ray tube where the exciting radiation is generated. And here is the hemispheric electron energy analyzer.
XPS is actually so sensitive that it can even tell the difference between oxidized and unoxidized states, as the inner shell electron's binding energy is slightly higher for oxidized atoms. For example, during the oxidation of iron, the binding energy moves from the initial 709 electron volts to 711 electron volts, which is a difference that we can measure. Now, if we wanted to map the elements on a sample surface, then we would need to use scanning photoelectron